We're now going to perform nodal analysis applying our understanding of KCL. A node is any point in a circuit between circuit elements, so for example between a voltage source and a resistor. We use nodal analysis on circuits to obtain multiple KCL equations which are then used to solve for voltage and current in a circuit. The number of KCL equations required is one less than the number of nodes that a circuit has. Usually, if a circuit contains a ground, whichever node the ground is connected to is selected as the reference node, and the voltages in the rest of the nodes are found with respect to this reference. We want to obtain these node equations to be able to interpret the circuit. Firstly, we express the current through an element in terms of the node voltage. Secondly, we apply KCL to all nodes bar the reference node. Here is a basic circuit incorporating two voltage sources, a current source, and two resistors. We can see there are three separate nodes with unknown voltages A, B, and C, as well as a fourth reference node connected to ground. Also note the orientation of the voltage sources. Node C is an example of a supernode, which is a node adjacent to a voltage source. That means we can find its voltage immediately. Remember to use convention as it's easy to get confused. Because of the orientation of the voltage source, we are subtracting the voltage at node C. Similar analysis can be performed to find the voltage at node A as it's related to node B as a supernode. Now we can get to forming the KCL equations. Assuming that current flows away from node A towards node B and C, the equation for node A is remember, the current flowing into a node is equal to the current flowing out. Now, we know the voltages in the nodes to either side of the 40 ohm resistor, so we know the voltage drop across it. We assume the direction of current flow to be towards the ground, so our equation using Ohm's law becomes the current through node C will be equivalent to the potential across the 10 ohm resistor divided by the resistance. Now we have the currents IB and IC, we can substitute them into our earlier equation for node A. We can further substitute the equations for VA and VC. Therefore, the KCL equation for node A becomes, noting that this is saying the 3 amps moving into the node are equal to the sum of the two currents moving out of the node, IB and IC. Solving for VB shows the voltage is 8 volts. Finally, finding the voltage at A, VA, is this plus 8 volts, 16 volts. Note that for all this analysis we've used the resistances and DC voltages for the sake of simplicity, but all this analysis is equally applicable with complex impedances and AC voltages.